Good morning, everyone. I'm David Brown from Lawrence Berkeley National Lab, and I'll be introducing our first speaker this morning. So Dr. Brian Spears is Technical Director for the Department of Energy's Genesis mission, which you heard about a little bit yesterday in Dr. Gill's talk. Genesis mission is a major federal effort to advance artificial intelligence, strengthen U.S. technological leadership, and support national security. Previously, Brian led AI strategy at Lawrence Livermore National Lab, where he advanced the use of AI for science and national security, and led modeling efforts behind the National Ignition Facility's historic fusion ignition milestone. He is a distinguished member of the technical staff at Livermore and has received multiple honors for leadership, research, and innovation in AI and high-performance computing, including 2 Secretary of Energy Achievement Awards. So please join me in welcoming Dr. Brian Spears.
All right. Good morning. Thanks for the kind introduction. It's a pleasure to be here with you all today. It's really exciting. I'm here to talk to everyone in the room, but really to the fellows. We're at a critical point in our computing history, really the history of the world. There's the confluence of a handful of events, and I will describe it later as a once-in-few-careers opportunity. So you stand on the precipice of a gigantic change in the way that we do science for national security, for discovery, and it's a moment where computing itself is going to change the face of our economy, our global security, and competition among great powers on the globe. So with that, I want to describe to you a little bit about the Genesis mission. If you've heard from Undersecretary Gill, then you'll have the scene set just a little bit. I'm going to dive a little bit deeper, and I'm going to do a thing that is fairly novel at conferences. I'm going to mainly stick to the abstract that I submitted for you guys. So it'll be in 2 pieces. There will be the technical parts of what we're actually doing inside the mission, and then I'll transition a little bit to what I think the future of work looks like because of it. And it's really a call to action for you guys to pick up the baton and make sure that we work together to change the world. Okay, the top level idea for Genesis and for what's happening in computing is that we have got to shorten the time from idea to impact. Historically, we have really highly functional scientific systems. We go from hypothesis to predictive simulation to a build of a part, a test, and close that loop, but it's quite protracted. It takes a long time. It has to go much, much, much faster. And for the first time, we have the capability to use artificial intelligence tools to shorten that time from idea to impact. So the recurrent theme today will be, what is it that we can do, what is it that you can do to go from idea to impact much faster in the name of discovery science for the United States, in the name of national security science for the United States. What is super clear at the current moment is that we're at an inflection point. I'm going to move this down a bit. That's a little live. Okay. We're at an inflection point for science in the national interest. 2 things are happening at the same time. First, the global security landscape is changing super rapidly. Handful of things happening there. We have an emerging global adversary. There's no other way to put it. A nation state who is potentially differently aligned than us and has said they're going to dominate the United States by 2030. Full and clear. We stand in 2026 on the precipice of 2027. Our international alliances are shifting. The rules-based global order looks different than it has at any moment since World War II. So 80 years of peace dividend for the West is starting to change and look different. And we have an accelerated pace for both discovery and deterrence on the national stage. There is a tripolar nuclear world with peer adversaries in Russia and China, and an underlining techno-economic competition where discovery science itself, not just the national security piece, is a key lever that countries are going to play in order to establish wealth, prosperity, and peace for the citizens of their nation. At the same time, we have that computing revolution in the background. There is no doubt whatsoever that AI is disrupting technical work. Everyone is picking up technological tools to use them, from folks in the private sector, standard people doing HR and operational research, but scientists at the frontier, cutting-edge mathematicians, our computer science community are picking up these things and moving at pace. And another thing has happened at the same time. Private funding is outstripping that of nation states. So hundreds of billions of dollars are going into compute. So for a room full of computing students, you operate in a system that is pressurized and energized in a way like no time in history, but that also brings what you're doing to the fore of international competition because it competes as an idea with those of other global economies and countries. And those two things together, a changing rules-based order in the world, plus a changing moment in computer science, make the sort of we nerds in the world put us in a position that we are not normally in, which is to steer the course of history directly and firmly. Okay, so AI is disrupting discovery and national security science, and we can see this really clearly. It's happening in a slightly different way than maybe we imagined it maybe 3 years ago. There are strong reasoning AI capabilities coming from industry. Those are fantastic and capable. But the thing that's really changing the way we do science is taking that AI and harnessing the powerful scientific assets that exist in the world, the ability to steer microscopes, telescopes, light sources, 3D printers, et cetera. So across DOE, we've recognized that there are critical injection points for the way that AI can change the execution of science and to shorten that time from idea to impact. So a pacing looks something like this. We can use AI to discover new materials. It is fantastic at generating hypotheses, helping us recruit resources, pull in atomic potentials, understand what lattice structures look like, et cetera. But once you discover a new material, it's not good enough to just drop it into an existing system. You have to redesign that system. So inside the Department of Energy, we've got AI agents and sentinels that can help us understand new materials that we have just built, can help us redesign those systems to take advantage of the new properties that we've just engineered, and build out a newly designed system that goes off and does its job much better in the presence of that new material. We've learned inside the Department of Energy and NNSA that it's not good enough to build a perfectly performant system that is infinitely costly to produce. You need to design for a system you can actually build in the real world. So we have AI agents that can sit on machines and watch the part be built, capture a digital twin of that part, and feed it back into our design engine and say, what is it that we do in our design to make the part much more manufacturable? And if we look to stage right, lots of these get deployed in high consequence systems, places where humans are operating in science facilities and are at risk, or systems that are national security systems. Those systems shall not turn to goop 3 months after we manufacture them. They've got to stand up to the harsh environments they live in. So often that puts constraints on those systems, and we go right back to the beginning and say, what is the material that we can design to make sure that this device functions, that the system is actually operating the way we want it to? So we wouldn't be here today grappling with this problem if it was good enough to work in silos. There are teams across the country working in all of these places, but what they need is an integrated capability so that we can rapidly discover these systems, so that we can go from idea to impact in greatly shortened time. And the nation really needs a system for translating those ideas in that way. And so the Genesis mission is exactly that. It's a whole-of-nation effort to harness AI for national impact. And one thing you should take away from that is it's not AI for AI's sake. It's great to bring the capability, but what we will be focused on is what mission is it for the United States that we're moving down the field? What are we discovering? What are we producing? What are we protecting that we use these systems to do? So the Genesis mission is going to do that, and there are two major goals that we're delivering on. The first is competitive dominance. We want to make sure that we can effectively double the impact of U.S. R&D GDP to lead to global competitiveness. Right now, the U.S. puts about 3.5% of its GDP into research and development. That puts it near the forefront of countries on the planet. If we could make that feel like 7%, it'd be the heaviest investment of GDP in R&D in technological history since we recorded those kinds of statistics. It would make it feel as if we had an economy that was twice as big as it was from the perspective of scientific R&D. On the national security side, we deliver what I call innovation overmatch. We need the ability to mint solution and mitigate threats on ridiculously short timescales so that we can outrun adversaries in any direction and domain on which they choose to challenge us. So those two ideas together, techno-economic dominance plus innovation overmatch, are the outcomes that we have to drive toward, but it comes from a scientific foundation. We've got to have a roadmap for what we go do in order to deliver that for the nation. So the Genesis mission is harnessing AI to deliver on an entire portfolio of those outcomes. So here is sort of the periodic table of the projects and programs that we're going to go after. They're divided into 3 lanes, an applied energy lane, a discovery science lane, and a national security lane. I won't read the whole chart to you, but they are things that will move the needle on the way that the US executes and moves in the world. So across energy, there are things like scaling the grid to power the American economy, making sure we can put power all the places that we need to go do that, or one that's near and dear to my heart, accelerating the delivery of fusion energy, making sure that there's fusion power on the grid that you can plug into, not just an experimental concept at a facility where you can blow something up with a laser, which I did for 20 years. Discovery science, things like realizing quantum systems for discovery, quantum sensing, building out quantum algorithms, or, quite importantly, making sure that autonomous laboratories that are AI-driven are a real thing for accelerating science and national security. And in the national security space, there are the problems that I've stared at for a very long time, making sure that we counter nuclear proliferation, that we have a non-proliferation program, that we can deliver on our strategic deterrent from idea to execution to impact on timescales that are relevant so that no one ever uses those technologies and we maintain the peace that we've had since the end of World War II. Okay, if you've got an answer for what you need to go do, a compelling set of problems to guide a nation in its scientific endeavor, then you had better have an answer for how you go do that. And the answer to how we go do that is what we call the Genesis platform. The goal there is really all encapsulated in the figure on the right. It is the purple box, brings strong scientific reasoning from frontier AI capabilities, and make it able to harness the boxes on the far right. The 8 decades of build-out of the Department of Energy since the Manhattan Project. High-performance computing, high-precision experimentation, and high-consequence production and manufacturing. All of those together in closed and self-reinforcing loops that are driven by AI in order to go from idea to impact inside these systems. It will capitalize on specialized models, unique data, powerful compute, all the things that live inside the Department of Energy. It will take advantage of the things that we have coming from industrial partners. So we do not aim to outrun OpenAI or Anthropic. We could do that with, I don't know, $10 billion of investment in a decade. We might get there. So there's no point in doing that. We're working in concert with our private partners to build out these capabilities. The platform is the toolbox that we'll use for these national challenges, and it's a toolbox that we will share that will be available to scientists and engineers like you guys. So what does it actually do? What's the point? The point is bring a few things to the table for scientists and engineers that you may have trouble getting your hands on right now. Raise your hand if on a regular basis you have access to frontier AI. You've got a GPT 5.5 high so I can see, like, okay, a good fraction of the room, but maybe half the room doesn't have access to the frontier AI that it needs. Our goal is to put those models in your hands, the platform, in the hands of DOE scientists. Once you do that, they've got to be able, through things like model context protocol servers, to connect to HPC experiment and production. We've got to be able to drive high-performance agentic workflows. Another question for the room. For those of you who are using frontier AI, how many of you have a persistent agent that's running? Something like an OpenClaw or Hermes agent? We've got 3. Okay, so mileage varies as you move down this stack. Frontier AI, lots of people have an eye on it. The capabilities for HPC experiment and production, that's why we're here and what we're here to do. When it comes to putting them into loops and steering them with frontier capabilities, we start to fall off. So the goal of the platform is to bring that to everyone across the country. This room, tens of thousands of scientists across DOE and academia and industry. If we do that, we're going to capitalize on our critical data and our unique subject matter expertise. That's one thing that I don't have to ask for you to raise your hands on. You are all here because of those capabilities. And it's the combination of that AI and its harnessed and steered capability together with the subject matter expertise and the critical data we can produce that we have to do. When we use that, we will train and improve key scientific AI models at the same time. So I said OpenAI and Anthropic will be out there producing their frontier capabilities. We won't do that. But if you need a foundation model for steering a light source or operating a neutron source in a mode that spans lots of regimes of imaging and physics capability, that's going to come from us. We will produce those things. Finally, as you'll figure out is the theme, this is the engine that enables the scientists to translate that vision into impact, both faster, because we'll be able to take out the computationally reducible parts and shorten them, but also qualitatively better, because there is first something that emerges from speed that's a quality all of its own. If you can do something 1,000 times faster, you can do it so frequently that it's completely different in your discovery loop. And then there's a qualitative improvement in and of itself, which is the things that I can't elucidate for you that you will think of. How can we operate our science enterprise in a way that we could not before because we have these capabilities? Okay, let me give you an example. You're going to see a sort of national security example, which is broadly applicable to applied energy, and then I'll show you a deeply science, discovery science example by itself. The Genesis mission is delivering capabilities as fast as we possibly can. This one's very cool science and national energy at the same time. Deliver a flight test vehicle for the nuclear enterprise using AI to go from idea to execution in months. This was a task that we actually gave a team, and it usually takes those teams about 2 to 3 years to go execute. They need to understand what a flight vehicle looks like. They need to understand how to build that so that it can operate at near sonic speeds, operate in re-entry conditions inside the atmosphere where things are heating up, build out electronics and avionics inside that, actually produce a prototype, etc. That 2 to 3 year period, we gave them 5 months to go do. It was daunting. But the shocking thing is that they did it. And they did it with the combination of both advanced manufacturing capabilities that we've been working on across the department, plus the platform that we gave them to harness those capabilities. So it actually looks like a familiar workflow. It's the scientific method. Hypothesize, build a prototype, judge whether it's good enough, produce it, test it, etc. But let me walk you through what it actually looks like. Over on the right, you see in those little spinning cylinders components that go inside the flight test vehicle. So that's going to hit about Mach 0.8 or 0.9 when we fly it. It gets very hot as it's flying through the atmosphere. These are stages that are designed by AI agents with topology optimization that are meant to either capture heat and soak up to raise the temperature on components, or to do the opposite and insulate and reject heat. And they're staged inside the flight vehicle. Those ideas come from thousands of AI-driven idea simulations. They go through a rejection filter to get rid of the bad ones and keep the good ones. And then a handful of those survive and actually go on to get printed. And they get printed at prototype scale so that we can see whether or not this device actually holds up. We can do preliminary tests on it. Next, there's a human in the loop. What we're not doing in any of these endeavors is taking the scientists out of the system. What we're doing is putting scientists in control of the system so they can grapple with huge amounts of data, a complexity from multi-stream, multimodal data, and a rate of advancement that ordinarily would make scientists feel like they were out of control. The goal is to put scientists in control and make sure that there's a degree of human judgment in there. So the fears about black box-driven AI don't come from our project. Then, once a human has looked at those and we've done optimization, we've done AI-driven prototype production, it goes to actual production scale. So there is a device that's 11 feet tall, weighs 1,500 pounds. Until like a couple days ago, it was sitting on the mall down the street. You could go pet it at the state fair thing that was running in the mall. But better than actually building the device with a bunch of AI driving and agentic steering that goes by MCP connections to these printers, the last stage was to actually test it. So that device, just a couple of weeks ago, at the end of this 5-month period, got hoisted up in a high-altitude balloon, dropped in the Utah desert, and did exactly what it was supposed to do. First time that I know of that an experimental system has been agentically AI conceived of, designed, printed, The actual telemetry and the metrology that is on the system, where sensors were placed and what measurements were captured, were AI designed, and that all went off perfectly. One thing that did not work, the parachute that was supposed to stop the system and slow it down was designed by a third party that we outsourced that failed, like completely. Like it had one job, which was to slow the thing down, and the thing it did not do was anything at all. So the system hit the ground in the desert at about Mach 0.9. It buried itself 20 feet into the ground through the rock water table, and we still got data back. So the engineers are quite proud. We have a conversation with the Department of War now about ground penetrators, and they're like, hey, you made a big-ass hole in the desert, and you didn't even mean to. Can we have a chat? So things happen when things go wrong as well as when they go right. But that is a pleasing demonstration of how we go from idea to impact in really short times. That's a 7x acceleration of an entire process that happens at the same time to be 15 times cheaper. So there's a theory of constraints and the old joke that you can have it good or right, you can have it fast or you can have it cheap. You get 2 out of the 3, but you can't have them all. With AI-driven solutions and modern technologies, you can have good and right, you can have fast, and you can have cheap at the same time. And we have to sort of spread understanding of how to do that and break that theory of constraints. Let me now shift to a completely different application where you'll see some of the same themes come forward. We asked a separate team to dramatically accelerate the pace of science discovery at a world-class light source. So it turns out that in light sources, there's this canonical problem that we have in working with users of those facilities. It's really cool to go in and say, I want to look at the microstructure of this thing. You can go do that. But if there's a mission need, a use case, it can be really hard in the timing. So folks would come from the microelectronics industry and say, we've got this chip that we want to probe deeply in. Your DOE light source is the only thing we can use to look at the structures at the length scales and at the depths that we need to probe it. And the answer would be, great. We can do that for you. We can take the images in a couple of days after the target is set up and we look at the chip. Then it'll be about 6 months of data analysis so we can produce the object that we looked at. And if we do that a couple of times, we'll have a good picture of what you're talking about. And the answer from industrial partners is we will be dead, defunded, and bankrupt by the time we finish the first measurement. So that's not really a capability. So the challenge is make these relevant to the mission speed and the pace that we're working on. So a team got that challenge, and they actually succeeded. They reduced that analysis bottleneck from 6 months to real time, a thing that used to take half a year in order to see an object appear from the diffraction patterns you can have in a light source, now happens in real time, and we'll show you in a little video that actually happening. But it happens because you can effectively violate that theory of constraints. The faster and better while also being cheaper is all happening at the same time. The example here is that there's about 1.3 terabytes of data that gets inferred on one GPU in real time. That used to be done by about 2,500 GPU hours with a bunch of computing that goes on in the background. That high-performance computing asset that takes forever to go do the image inversion, has now been reduced to a real-time asset that we can use with a lot of AI analysis to help that actually happen. So this is shortening that time to impact again, and it has delivered an entirely new capability. So let's stare a little bit at what's going on. There's a movie playing with some really clever audio over the background that we really are not going to take a chance to look at. But what you're going to see in here is the entire process of executing this workflow. There's an idea that somebody wants to measure a particular object. There's a target that you'll see moving around, which is the actual chip. It's a microelectronic device that we want to get probed. There's a piece of this that is sort of the computationally irreducible part. Right now, it still takes time for somebody to load these systems, to put them in the beamline, to align the system. It is coming that we will automate pieces of that so that there are robotics and automatic capabilities for doing the alignment. But then you get to this stage. Target is in there. The diffraction pattern is what you see at the top. That means nothing to humans. And in real time, the images that you see on the right and here are the actual object reconstruction showing up at the pace that it actually happens. So that's a 6-month effort. All of these capabilities now run at SLAC, at Brookhaven, at Argonne, and across the country. It runs on top of a foundation model. Those specialized models that I said we would build inside the Department of Energy, we will build those. We'll put them in these workflows, and then they'll operate in our networks to accelerate the way that we do science. I'll point out the thing that actually matters is the impact. So it's really great that it goes fast, but what does it fundamentally do for us? It gives us the capability to do fully three-dimensional, non-destructive evaluation of components at node sizes, at length scales, that are now relevant for that mission. It turns out that going from 6 months to the real time is about 1,000 times speed up, and the resolution, the clarity of the images that we can get is about 10 times better than what we could before. So no upgrade to a facility. It's 1,000 times faster, 10x better, and it's cheaper because it's running on 1 GPU instead of 2,500 GPUs. So you should be asking, where does the rabbit go into the hat? It doesn't. It's there because there are new technologies that we brought to the system that are just fundamentally changing the trade space that we're operating in. Okay, there's a ton of stuff that we can do, but there's a lot that we cannot right now. So we are far from fully capable. What can we do? AI plus HPC plus instrument. So you saw that. That happened in the Ares-Tide flight vehicle simulation or project. It happened in the Synapse project, the light source project. What we can't do is fully close going from the instrument back to the AI and making sure that that loop can operate. We know how to do it. We're just not there yet in our execution and implementation. The next thing that we cannot yet do is have that closed loop run multiple times, 5, 10 times, 100 times, have it run for days. There we know mostly what to do, and there's some R&D that has to be done. Agents have to be able to not get confused on their task for longer run times, which is happening in industry, it's happening in science, so we're working on those. The thing that we really cannot finally do, which is our ultimate goal, is have that loop run not just with one instrument, but 2, 3 instruments, other devices, an entire fleet of those things operating in a facility. In fact, an entire network of facilities across the United States. And so when I refer to the Genesis platform at the top, what we mean is AI running at frontier laboratories, coupled with AI and compute running in our data centers, pushed out to the edge in laboratory and manufacturing spaces where we can drive these fleets with cross-facility interaction. And what you see emerge is something that we often refer to as the world's most sophisticated and exquisite scientific instrument. Because by definition, most of the facilities that we're driving inside the Department of Energy and across the United States are world-class and the best of their kind. You integrate those together with our data resources and compute capabilities, and you have emerged a singular resource for the United States, for the department, and for the scientists who are actually using and executing that. So we know how to do this. It is not high technological risk. So I come from the fusion community. We made a 6-decade bet that you could put laser energy on a fusion target and get more energy out than what you put in, without it being completely clear that the energy balance at the microscale was actually physically possible. We had really good reasons to expect that that was the case. That's hard. Turning that to commercial fusion power, where you have to do it at 10 times per second, now that we've done it about 10 times in human history, that's super hard. These problems are difficult, but we've got a roadmap. We know how to get it done. This is low technological risk by comparison. It's now a question of national will and of energizing researchers like yourself to go make this the way that we do science in the future. Okay, so let me now transition from the clear picture of what we're doing to the things that we can do together and that you guys have to do. We stand at this moment where the way that we do scientific work is fundamentally changing. And it's changing in these 3 ways. First is at the level of abstraction. No longer are many people writing character by character code. It's clear in programming that we've risen up the abstraction layer. So we don't write machine language anymore. Anybody in here working on compilers? Has anyone ever designed a compiler? 1, okay. So we still need compilers, so keep going. The rest of you don't start writing compilers, right? We don't write compilers anymore. We moved up the stack of compiled code, interpreted code. Now there are folks operating, most of us, vibe coding at the top. That used to be a negative phrase, like vibe coders who don't know what they're doing. There are lots of us who are embracing it as like the way to go forward. Because what you actually do is go out and engineer the system that you're trying to build in your head use a machine to write out the infrastructure underneath it. It's just another layer of abstraction. What it means is defining outcomes, those impacts that you want to have and the way you get there, and the approaches, not the actual task. Don't explicitly say, here are the steps to take. Define where you are, define where you want to get to, and use the computational capabilities that you have to figure out the route. It's a lot like Google Maps. No longer do we have a book of maps in the glove compartment of our car where we find our route from A to B. We use the technologies that we have available. What's really important, and it will be important for you as you build out your careers, is that you now have to know what success looks like. You have to be the folks who make the definition of where you want to be, of the thing that you actually want to build and work on. And that's a way of operating that we have historically reserved for principal investigators, for the folks who have spent 5 years in the field, 10 years in the field, have built up a small team around themselves. It's been their domain to see what success looks like, to define those outcomes, and to start building the plans to do it. You now have the burden of doing that right now. But you also have the opportunity that in your toolbox are a bunch of silicon friends, AI agents that can be your team, that are going to go help you do that. And it's my job to give you the toolbox for you to use, but yours to understand this change. Next, an opportunity and a risk at the same time is the change of pace. So new tools emerge now on something like a 3-month timescale. We are now approaching the 3rd set of 3 months in this calendar year. And if you look back to where we were in January in AI space, it had been the year of the agent in 2025, and commercial tools were just starting to roll out. Now, almost everyone is using a Claude Code or a Codex. There are these persistent agent things from Hermes and OpenClaw. We have networks of these things working. An interesting anecdote, on the plane last night while I was using Wi-Fi, my persistent agent named Crush from Hermes was talking to that of Rick Stevens and a few other folks working in our enterprise, and our agents set up a meeting by email with each other, and my agent defined an agenda for what they were going to do to work on an emergent memory system for agents that we were working on. It was pretty cool. They looped me out. I had asked to be put back into the email system. They grow up fast. But it was shocking to see these conversations happening with real engineering architectural outcomes coming from the background. So that pace is absurd. Another thing you have to recognize is that the mission, the steady part, needs responses on completely different timescales. It's fast compared to any time in history, so maybe on the 3-year timescale, the way that we do science is changing, but you'll have to balance this very fast, how do I know what the frontier looks like, with the steady, what is it that is being called to be done in my scientific field, in my national security mission. And then finally, another thing that's changing for the way that we do work and that you will have to build a game plan for your career in is the playing field. It's just different than it has been. Go, if you haven't, check out the endless frontier vision that emerges somewhere in World War II from Vannevar Bush. That sort of sets up the triad of academia, industry, and government working together in the scientific endeavor. It's very easy for us to name the 3 corners of that triad because of the endless frontier vision. That's not necessarily a given, that we have balance between those 3 things, and it's changing. Right now, private industry is doing things formerly reserved for the public sector and nation states. I mentioned already funding at the tens of billions to hundreds of billions of dollars level. The build out of infrastructure that is on par with what happens in nation states. The hiring and recruiting of interdisciplinary teams that used to be the purview exclusively of the Department of Energy is now happening in startups across the private sector. There are also transformational tools that are coming from the outside. We used to build a national ignition facility, $3.5 billion laser facility. If you look in the fusion space, Commonwealth Fusion is building an enormous machine. Pacific Fusion is building an enormous pulse power machine that could be a national security asset. It could be a prototype for a commercial fusion plant, and it's coming from outside the department. So what's true is that we still in the Department of Energy community have got to be the fastest on translating these emerging methods to impact. One thing that I'll go into just a little deeper is that only we in the national security space are the public-minded stewards of what the nation needs. The private sector cannot see that. They are conflicted with incentives that are fundamentally commercial, and we have an obligation on the public side to look at this through a different lens and to provide a different outcome for the United States. You've got literally a once-in-a-few-careers opportunity. A moment like this will not happen again until there is another scientific revolution. If you're going to go do some other reading, check out the theory of scientific revolutions from Kuhn. Basic ideas: there are normal operating procedures in science where we're refining how we get done, and there are these abnormal systems of disruption, and we are in one of those right now. You can plan for what happens in those normal procedures. You cannot plan the disruptive event. So you have one handed to you right now. You've got to take advantage of it. So only we can do what the country needs. With all of that changing landscape, the changing pace, the changing tools, abstraction levels that we're operating at, there are a couple of things that, as part of this community, and many of you will be longtime members of this community, you've got to do. First, we have to operate at the intersection of mission, capability, and scale. That is uniquely us. And the first one is probably the most important, sort of a steely-eyed focus on mission for the country. What is it that the United States has got to do? Think back to that periodic table of problems and portfolio of important challenges that we had at the top. What is it that we have to do for the country to move the needle on how we compete? The second is you've got to have a deep knowledge of the solution. AI will not do that for you. How are we going to do it? What is it that you need? What are the ingredients that have to be brought together? The chemists, engineers, physicists, all in the same box. What are the tools and techniques that we have for the approach? Then an understanding of the power of the labs. You are getting to see for the first time what can happen inside the Department of Energy. Start thinking about the question, what happens if you activate 40,000 scientists? That's what we can do inside the Department of Energy. So artificial intelligence is great, but right now we've got a capacitance of 40,000 scientists and engineers who could get excited about an idea that you could have that could become the central focus for what this nation needs to do in the future. So I talked about raising the idea of the abstraction layer, like move up, don't say do this task, but try to execute this goal. Start wondering now at scale. What would it look like if we were moving toward that goal, but not just with me, not just with my team of researchers and my supervisor, but we had an idea that was so exciting, it would animate 40,000 researchers across the country. That's the kind of capability that we still need. And at the intersection emerges the public concert, the public conscience. What is the right way to go do this? There are folks who can think about how to do this, but there is nobody outside the public sphere that will be balancing what is there for the good of the country, plus what is the exciting science, plus what brings those together at the pace and scale that can actually make it matter. So you have to maintain the national interest in your understanding of progress. It's just imperative. Okay, another idea, something that I wish someone had said to me early in my career that I'm going to say to you. You are responsible. This reminds me of a thing that happened to me when I was a kid. So there was a public service announcement, and Smokey the Bear would come on to a commercial on television. Like, he used to broadcast over airwaves to your TV. And Smokey the Bear would say, only you can prevent forest fires. And so I was 6 years old and thought, what the actual hell? How is it that I am the only one who can prevent forest fires in this whole country? This seems ridiculous. So it turns out that my wife also thought the same thing and may explain why we are married, because we have a similar worldview. Okay, but only you can prevent forest fires. The point is, you are a leader right now, and you have more power than you think. It's your job to think big at those scales that we were talking about. You can already be a fire starter. You can have an idea that your advisor, that your supervisor can recognize the good in, can be the amplifier for your idea, can get you going to that 40,000 person scale idea. That's in your control right now. The other thing that you have to know is that no one will do it for you. Like, you are the adult in the room now. It's your job to have the idea, and no one can get your brilliant idea out of your head and into the other folks' heads in the world. That's on you to do it. You also cannot do it alone. Nobody does. It's the power of the teams. Is that 5 minutes? Yeah, perfect. It's the power of the teams that actually matter. No one has all the answers, but you have to be sure that you have some. And the way to have those answers is to be better prepared than everyone else. You have to read deeply. You have to understand the state of the art. You have to have an idea in the room so that when somebody says, hey, what should we do? You've got 35 answers. Like, be ready to go. It takes a lot of thinking to have that perspective. It's not good enough to have an uninformed opinion. Our jobs are to have the most deeply informed, crystallized expert opinion that we can possibly get. And if you don't have it, that is the fun part. Go figure out how you have the best, most clearly framed idea for how to go attack these big problems in the world. Next, you gotta be able to communicate your idea. It's amazing. We have this ability to wirelessly communicate ideas from inside our heads to inside other people's heads. It's fantastic, and you do it by speaking, by writing, by drawing pictures at the whiteboard. You have to be the most effective communicators on the planet to take an incredibly complicated idea and a vision that you have in your head and put it in someone else's head in a way that they understand it, in a way that inspires them to go act because they think, yeah, I see it. That's a great thing to do. So don't underestimate how important the communication capabilities are. That's on you. And finally, just say it. Like, once you've got the idea, you have to just say it. I can now think of 5, 10, 15 times in my career that I've stood outside a room of people in places from the Situation Room at the White House to briefing rooms at Congress to leadership rooms across national labs and thought, am I actually going to walk into this room and say aloud this preposterously huge idea? And yeah, you just have to do it, because if you don't, then it can't happen. You cannot make it happen. Okay, a couple of questions, and then we'll go to the wrap up. But you should ask these questions as you think through it. Like, what outcome would fundamentally change how things are done? What actually matters? What actions would it take to deliver those outcomes? Like, how do you get there? These are things that I ask myself all the time. What happens if you engage at scale? Like, what does big look like? Not like kind of big, like what does absurdly nation scale, globally big look like? And if you fall 2 orders of magnitude short, you'll still change the world. And then what happens if someone gets there first? That one's super powerful because it animates you. If you would like that outcome and you would really not like someone else to have that capability first, use that to get folks to understand. And then the last thing, what's the dumbest possible first step that you can take? I say this all the time. I don't mean like literally dumb, like a bad idea, but what is the simplest first step, the hello world, that you can take to show that that gigantic world-changing idea actually has proof of principle? Just connect your thing to that person's thing and make it work at small scale. Go from there. That's super critical. Okay, that's the end. We've got to be the first to deliver this new system for translating ideas to impact. And 2 major themes for the day. First, we're building that so that we can maximize the impact for the US. And second, you guys have to do it. Only you can prevent forest fires. You are building you to maximize the impact for the US. Okay, with that, thanks.